So it's not a good idea to drink salt water because it will cause you to become dehydrated. And you may think, well, why? How can I become dehydrated? I'm drinking water. Well, it has to do with osmosis, which is the flow of solvent from a less concentrated solution to a more concentrated solution. And your book doesn't get into the energetics of this and why this happens. So we're just going to go through what happens, and then if you're curious, I'll try to explain why. So this happens when you have a solution with a high concentration of solute, and that is going to draw solvent out of a solution with a lower concentration. So we say that seawater is a thirsty solution. Well, how could a liquid be thirsty, right? Here's an illustration of your intestine. Okay, nice, huh? It's a nice clean picture, though. So the walls in your intestines are semipermeable membranes. And what that means is that there are tiny pores in them that are large enough that water molecules can get through, but they are not so large that solute molecules such as sugar and ions can get through. So on the outside of your intestine, here is a lower concentration of salt, of solute in general, and on the inside, if you're drinking salt water, then what you have in your intestine has a high concentration of solute. And basically, this is nature trying to equalize things. We've got a separation of concentration here, and it's trying to get them to be equal. The salt cannot move this way, so the solvent moves this way in an effort to dilute this solution. Like, that's really concentrated. This is not concentrated. Things want to be the same. Okay, so the water will go this way. Well, it's pulling water out of your body. You're drinking the seawater because you're thirsty, but it actually causes your body to lose more water than if you didn't drink anything at all. So it actually dehydrates you. This is called an osmosis cell, and what we have here is a tube. It's shaped like a U, and here in the middle is a semipermeable membrane. Again, that allows the solvent to go through, but not the solute. So on one side here we have pure water, and on the other side we have something with a solute in it. We'll call it salt water. And what's going to happen is osmosis will occur, and the water molecules will travel to the saltwater side much more than they will travel back. There is an equilibrium going on here, but in general it will move to the more concentrated side. And so what you'll see is you'll actually see the level of liquid in this side of the tube rise up. And if there was no semi-permeable membrane in here, that would not happen. You don't just see water in one half of the sink rising up above water in the other half of the sink, do you? It just doesn't happen. Gravity pulls it all down to the same level. But it's trying to equalize the concentration here. And so the water will flow this way, causing the liquid level on this side of the tube to rise and this side to fall. Well, when we have a difference in liquid levels here, there is a difference in pressure. Gravity is pulling down more on this side than on this side. And so this difference in levels represents a pressure, and we call that osmotic pressure. It's the pressure that arises from osmosis. Another way to think of what osmotic pressure means is it's the pressure that you would have to exert pushing down here to cause this to go back to where it started. It's the amount of pressure needed to oppose the osmosis. So something that has a higher concentration here is going to have a higher osmotic pressure than something that has a low concentration. Osmotic pressure is a colligative property. It only depends on the number of particles, it doesn't depend on what they are or how big they are or anything. The more concentrated the solution, the greater the osmotic pressure. And your body makes use of this with its semi-permeable membranes. It makes very good use of this. if you put a living cell into seawater, it loses water through osmosis and becomes dehydrated. This can happen with blood cells too. So here's a photograph, magnified obviously, of normal red blood cells. They kind of have this donut shape. So here the red blood cells are in a solution where the concentration of solute is the same as the concentration of solute in the liquid inside the cell. We say that's an isotonic solution. I'm not going to quiz you on these words. But if you're headed into the medical field, you'll hear about this. So that's called isotonic. In the hospital, if they give you an IV, they're not pumping water into your veins. They're pumping 0.9% sodium chloride solution. It's called normal saline, and it has the same solute concentration as the plasma in your blood does. So when it comes in, your blood cells, your red blood cells are good with that. If you put red blood cells in pure water, now you have solute concentration inside the cell and no solute on the outside. And so the water is going to go to the more concentrated solution, and the red blood cells are going to swell. And they will continue to swell and eventually burst. Okay, so red blood cells bursting is not a good thing in your veins, right? So you'd never want to have pure water injected into your veins. The other situation that can happen is if your red blood cells are in a solution that is more concentrated, and that will cause the water to flow in the other direction. And the red blood cells will then shrivel up and get all small because the water is leaving them. They'll get all dehydrated. This happened to me when I was a newlywed. My husband's Japanese, and his family has some interesting little food delicacies. Have you ever had teriyaki hot dogs? They're actually really good. So you make teriyaki sauce, and you score the hot dogs a little bit. If they're spiral, then they're prettier, which is important, apparently. Anyway, so you boil the hot dogs in teriyaki sauce, and then you eat them over rice. And it's just a lot fancier than hot dogs on a bun or plain rice, and it's a nice, cheap food. And so my husband was in graduate school, and I made dinner, and he was late coming home as usual. And so I left the hot dogs in the teriyaki sauce. Do you know what's in teriyaki sauce? It's about 1/3 sugar and 1/3 soy sauce, which is very high in sodium, then 1/3, water or wine or beer or something. So very high solute concentration. So I had some serious osmosis going on with these hot dogs, and by the time he came home, they were hard as rocks because it had pulled all the water out of these poor hot dogs. So I learned something that night. If you're going to, keep the hot dogs, take them out of the teriyaki sauce and store them by themselves so that doesn't happen to them. But this principle can be used in cooking for various reasons. Sometimes you have a vegetable that you want to fry that has too much water in it. So if you soak it in salt water, it will draw some of the water out, and then when you fry it, it won't make such a big mess. So there's all kinds of things. But, you don't want to leave your meat soaking in a marinade too long, or it'll pull all the water out, because plants and meat are from living tissue, and they're full of semipermeable membranes, and the water will just come out of them like that. And there we have chapter 13. So chapter 13 in review. Those are the skills you should be able to do, and